12. Welcome to Compressible Flow. Today, we enter a new regime of fluid behavior, where density is no longer constant, and the speed of sound is no longer a background number. Compressible flow is not just about high-speed jets or rockets. It's about understanding how gases behave when pressure changes can no longer be ignored. Unlike incompressible flow, here even small pressure differences can cause significant changes in density. This makes the equations more complex, but also more powerful. It's the key to designing nozzles, diffusers, and understanding shock waves. As we begin, shift your mindset from constant density to variable density. Embrace the role of Mach number, isentropic relations, and compressibility effects. This is where the beauty of thermodynamics meets the rigor of fluid mechanics. Let's explore how air moves faster than sound, how shock waves form and interact, and why compressibility changes everything at high speeds. Welcome to the fascinating world of compressible flow. 1. Introduction to compressible flow. Compressible flow begins when changes in density can no longer be ignored. This happens especially in high-speed gas flows, like those in jet engines, rockets, and supersonic wind tunnels, where even small pressure differences cause measurable shifts in density. At this point, fluid mechanics merges with thermodynamics. The behavior of compressible flows is governed not just by momentum conservation, but also by energy and entropy. We use the ideal gas law, assume constant specific heats, and begin looking at temperature and pressure as intertwined with velocity and density. To study compressible flow is to enter a new fluid domain, where shock waves, expansion fans, and Mach numbers take over. You're no longer dealing with fluids that just move, you're dealing with fluids that breathe, compress, and explode with energy. Understanding compressible flow isn't just academic, it's the foundation for designing aircraft, spacecraft, gas turbines, and even understanding atmospheric re-entry. We start here with the basic concepts and assumptions and build toward a complete understanding of high-speed flow physics. 2. Key concepts in compressible flow behavior. Before we go deeper into compressible flow behavior, we must understand stagnation properties because they serve as reference points in high-speed flow analysis. Stagnation means the condition a fluid would reach if brought to rest isentropically, meaning without heat or work interaction and with no friction losses. Let's begin with stagnation enthalpy, defined as the sum of static enthalpy and kinetic energy. H naught equals H plus V squared over 2. This equation tells us how the energy of motion is converted into thermal energy as the flow decelerates. In adiabatic flow, without work input or output, this stagnation enthalpy remains constant. From that, we derive stagnation temperature. If we slow down the flow adiabatically to zero velocity, the kinetic energy turns into internal energy, increasing the temperature. That gives us T naught equals T plus V squared over 2Cp. This relation becomes crucial in applications like nozzles, diffusers, and turbomachinery. Stagnation pressure is another critical concept. For isentropic flow, the stagnation pressure relates to static pressure and temperature by the equation P naught over P equals T naught over T to the K over K minus 1. This allows us to track pressure changes in varying velocity fields, especially across shock waves and converging-diverging passages. Together, these stagnation properties act like anchors, tying thermodynamic and fluid dynamic properties together. Mastering them allows you to confidently analyze everything from jet engines to high-speed wind tunnels. 3. One-dimensional isentropic flow. Let's now focus on the foundation of high-speed gas dynamics, one-dimensional isentropic flow. This is where we analyze compressible flow, assuming no heat transfer, no friction, and constant area or smoothly varying geometry. The flow remains reversible and adiabatic, perfect for understanding ideal performance limits. To begin, we define the speed of sound in an ideal gas. It is the rate at which pressure disturbances travel, and it depends on the thermodynamic state of the gas. The formula is C equals the square root of kRT, where K is the specific heat ratio, R is the gas constant, and T is the absolute temperature. This means the speed of sound increases with temperature and depends on the molecular characteristics of the gas. Next comes one of the most essential non-dimensional parameters in compressible flow, the Mach number. Defined as the ratio of flow velocity to speed of sound, Mach equals V over C. This simple-looking ratio changes everything. When Mach is less than 1, the flow is subsonic. When Mach equals 1, it's sonic. And when Mach is greater than 1, the flow is supersonic. Mach number tells us whether a flow can communicate upstream, how disturbances propagate, and whether shock waves or expansion fans will appear. Isentropic flow models may seem idealized, but they give engineers powerful insight into nozzle flows, diffusers, and compressible piping systems. With just Mach number and a few basic relations, you can estimate pressure, temperature, and density changes without complex simulations. This is the baseline of understanding before we introduce shocks and real-world losses. 4. Flow through nozzles. To understand how compressible flow behaves in practical systems, we must study nozzles, devices that control and accelerate gas flows using area change. There are two key types of nozzles, converging and converging-diverging, and each serves a different purpose depending on the desired flow regime. Let's begin with the converging nozzle. As gas flows through a narrowing cross-section, its velocity increases while pressure drops. However, there is a limit. When the flow reaches Mach 1, also known as sonic conditions, the nozzle becomes choked. Beyond this point, increasing downstream suction or lowering exit pressure will not increase mass flow rate. It's as if the nozzle reaches a traffic jam of molecules, maximum mass flow, but no more speed increase. You simply cannot go supersonic with a converging nozzle alone. To go beyond Mach 1, we need a converging-diverging nozzle, also known as a Laval nozzle. In this design, the flow accelerates to Mach 1 at the throat, the narrowest part of the nozzle, and then continues to accelerate into the supersonic regime in the diverging section. At subsonic speeds, flow accelerates in converging sections and decelerates in diverging ones. But once the flow passes the throat and becomes supersonic, everything flips. Now the flow accelerates in the diverging part, and pressure and temperature continue to drop. The Laval nozzle is the core of rocket engines, supersonic wind tunnels, and gas turbines. It shows how geometry can be used to manipulate energy conversion, turning thermal and pressure energy into velocity. It's not just a pipe, it's a precision machine for controlling high-speed gas flow. 5. Shock waves. When a compressible flow encounters abrupt changes, either due to geometry, pressure differences, or directional turns, the result can be a shock wave. Unlike gradual pressure waves, shock waves are sudden, intense, and irreversible. They mark a sharp boundary in the flow field where fluid properties jump almost instantly. Let's begin with normal shocks. These shocks stand perpendicular to the flow and occur when a supersonic stream is forced to decelerate to subsonic speeds. Across the shock, velocity drops dramatically, while pressure, temperature, and density increase. Entropy rises as well, making the process irreversible. Interestingly, although static properties increase, the stagnation pressure drops due to the irreversible nature of the shock. Oblique shocks are a more general case where the shock wave forms at an angle to the flow direction. These are characterized by two key angles, the shock angle, beta, and the flow turning angle, theta. Depending on the conditions, the oblique shock can be weak or strong. Weak shocks are usually desired because they cause smaller losses. Strong shocks bring larger property changes, but higher losses. After passing through an oblique shock, the flow might still be supersonic or may become subsonic. Then we have the Prandtl-Meyer expansion waves, which are the opposite of shocks. Instead of compressing the flow, they allow it to expand. These waves occur when supersonic flow turns away from the original direction, like in the divergence section of a nozzle or around corners. The expansion is smooth, nearly isentropic, and causes the Mach number to increase, while pressure and temperature drop. Shocks and expansion waves define the structure of supersonic flows. Mastering them is essential for designing supersonic aircraft, propulsion systems, and high-speed aerodynamic surfaces. In compressible flow, smoothness is rare. Sharp transitions, like shocks, often govern the rules.
6. Rayleigh flow. Rayleigh flow is a model that describes compressible flow in a steady, one-dimensional, constant area duct where heat transfer occurs but friction is absent. This idealization is especially useful for analyzing combustion chambers, afterburners, and any device where heat is added or removed from a high-speed gas stream. As heat is added to the flow, the stagnation temperature and enthalpy increase. If the flow is cooled instead, these properties decrease. However, the effects of heat addition differ depending on whether the flow is subsonic or supersonic. In subsonic flow, adding heat increases both velocity and Mach number. The fluid accelerates, and as a result, density and static pressure fall. This behavior can be counterintuitive. Adding energy to the flow causes the gas to expand and speed up. In contrast, for supersonic flow, the opposite occurs. Adding heat actually decelerates the flow. Velocity and Mach number drop, while density and pressure rise. This is because the energy added increases random motion, temperature, more than directed motion, velocity, effectively slowing the supersonic stream. Interestingly, the temperature doesn't keep rising with more heat. There's a peak point, and it occurs when the Mach number equals 1 divided by the square root of K. For air, that's approximately Mach equals 0.845. This condition represents the thermal choking limit. Beyond it, further heating will not increase the temperature and may even lead to instability. Rayleigh flow is a powerful tool for understanding thermal effects in propulsion systems. Whether you're analyzing jet combustion or cooling stages in hypersonic vehicles, this model helps predict how heat shapes velocity, pressure, and flow regime.
7. Fano flow. Fano flow is the compressible flow model for situations where friction is present but there is no heat transfer. This makes it an adiabatic flow with internal irreversibility due to wall shear, common in gas flow through rough or long ducts like ventilation systems or engine intake lines. The key difference from Rayleigh flow is the role of friction instead of thermal energy. In fanoflow, the friction affects velocity, pressure, and Mach number, but the stagnation temperature remains constant throughout the duct. However, the stagnation pressure steadily decreases because friction dissipates mechanical energy into internal energy, increasing entropy. In subsonic flow, friction has a counterintuitive effect. It accelerates the gas. As friction extracts energy, pressure and temperature fall, but the flow speeds up and the Mach number rises. Eventually, the Mach number approaches 1, where the flow becomes choked. No further acceleration is possible despite continued friction. In contrast, when starting with supersonic flow, friction slows it down. The Mach number decreases, and temperature and pressure rise. Again, the process moves toward Mach 1. Regardless of starting condition, fanoflow evolves toward a choked condition where Ma equals 1, and that's the natural limit of flow rate for a given duct and friction level. Once the flow becomes choked, any additional friction shifts the location of the shock wave upstream if one forms. This principle is used in analyzing shock boundary layer interactions and understanding how flow adjusts in real pipes and gas delivery systems. Fanoflow reminds us that even without adding heat, flow properties can change dramatically purely due to the roughness of the path the fluid takes.
8. Property relations. Compressible flow is rich with interconnected variables: Mach number, pressure, temperature, density, and area, all shifting together as the flow evolves. To make sense of this complexity, engineers rely on established property relations that define how these variables behave in different regimes of flow. These relations are not guesses. They come from analytical derivations based on conservation laws, thermodynamic principles, and ideal gas behavior. For isentropic flows, we have elegant equations that show how area ratios relate to Mach number and how pressure and temperature drop as the flow accelerates. For shock waves, both normal and oblique, the relations help us quantify sudden jumps in properties. Across a shock, you can precisely calculate the downstream Mach number, pressure rise, density jump, and entropy increase. Rayleigh flow introduces heat transfer, and we track how adding or removing heat affects velocity, temperature, and pressure, depending on whether the flow is subsonic or supersonic. Fanoflow, driven by friction, gives us different property changes. Here, Mach number evolves toward unity, and pressure losses are inevitable. These relations can be expressed through formulas, but more often they're presented in ready-to-use tables. These tables, whether for isentropic ratios, shock properties, or Rayleigh and fanoflow, make analysis practical and efficient, especially when dealing with design or quick estimates. In applied fluid mechanics, you don't memorize all the equations. You understand the behavior, then use property tables to find exact numbers. That's how theory becomes a tool for design.
9. Choking phenomena. Choking is one of the most important and unintuitive behaviors in compressible flow. It defines the limit beyond which no increase in driving force, be it heat addition, pressure difference, or friction, can increase the mass flow rate. Once the flow reaches sonic speed, the system becomes choked and cannot accommodate any more flow without major structural or condition changes. In Rayleigh flow, which involves heat addition in a constant area duct, the choking phenomenon occurs when the Mach number reaches 1. If you continue to add heat beyond this point, the flow cannot accelerate further. In fact, the additional energy causes instability and a reduction in mass flow rate. The system has reached its thermal flow limit, and the flow becomes choked due to heating. In fanoflow, where the limiting factor is friction in an adiabatic duct, a similar condition arises.
As the flow progresses along a rough duct, friction causes pressure to drop and Mach number to rise in subsonic flow, or the reverse in supersonic flow. Eventually, the flow will reach Mach 1 regardless of the starting condition. At that point, it is also choked. Any additional friction does not change the mass flow, but pushes the flow toward greater entropy and moves shock waves upstream if they exist. Choking is not just a boundary, it is a control mechanism. Engineers use this property to design systems with predictable flow rates, such as nozzles, diffusers, and gas lines. Whether it arises from heat or friction, choking imposes a hard ceiling on what your system can deliver unless the upstream or downstream conditions are fundamentally altered.
10. Summary of effects. When studying compressible flow, it's easy to get lost in the equations, but ultimately what matters are the patterns, the consistent ways that velocity, Mach number, temperature, pressure, density, entropy, and stagnation properties respond to different physical conditions. This summary table brings clarity by showing how these variables behave in 4 key scenarios: Rayleigh flow and Fano flow, both in subsonic and supersonic regimes. Start with subsonic heat addition in Rayleigh flow. As heat is added, velocity and Mach number increase. Temperature rises initially, but drops after the flow hits the critical condition at Mach equals 1 divided by square root of K. Pressure and density drop, entropy rises, and stagnation temperature increases. However, stagnation pressure drops due to irreversibilities introduced by heat addition. Now, consider the opposite, supersonic heat addition. Here, heat slows the flow down. Velocity and Mach number decrease, while pressure, temperature, and density all rise. Entropy increases again, and stagnation pressure drops, just like in the subsonic case. Stagnation temperature still increases because energy is being added. In Fano flow with subsonic entry, friction causes the flow to accelerate. Velocity and Mach number increase, while temperature, pressure, and density decrease. Entropy still rises, and stagnation pressure falls due to frictional losses. However, stagnation temperature remains constant because the process is adiabatic. Lastly, for supersonic Fano flow, friction causes deceleration. Velocity and Mach number drop, but temperature, pressure, and density rise. As with the other Fano case, entropy increases and stagnation pressure drops, while stagnation temperature stays fixed. This summary is more than a memorization tool. It's a diagnostic map. If you know what's happening to one property, you can infer the rest. That's the power of understanding the physics behind the patterns.